things to keep in mind as we move into the next couple of sections. You are going to be using these calculators to get your homework done. You're going to really need to make sure you do that in class. There are some calculator apps that I can tell you about that you can download on your phone that allow you to do these same things. But I will warn you that I think in the spring semester there are some calculators, things that no apps can do, so you're going to have to be able to get your stuff done in class. The first thing I want you to do is clear the memory, so we kind of start building that good habit. So put your phones down. Make sure you know how to clear the memory. Does anybody know how to do that? Yes, second plus 712. Second plus 712, and it should say that your RAM is cleared. This will be important moving forward when we start entering some data values into lists and so forth, okay? But just want to build some good habits, so by the time we get there, you're good to go. Okay, once your memory is cleared, you can kind of just put your calculator off to the side for a second. And the title of the notes is Normal Distributions, Finding Areas from Values. Well, I want to start off with a little bit of a review because it's been a few days since I've seen you. I want to make sure for today's lesson that you can sketch a normal curve really quickly and put the mean where it goes and the standard deviation and go 1, 2, and 3 standard deviations out and answer this question right here that says, what proportion of the area under the curve is less than 8? So that's the goal. If you're reading this, it says to sketch a normal distribution curve with a mean of 6, standard deviation of 2. If you've been doing your homework, you've been having plenty of practice drawing these. So you're going to draw your horizontal axis. You're going to get your normal curve, which is a bell-shaped, single-peak, symmetric curve. Mu is 6, so the mean is 6. That's going to go in the middle. The standard deviation being 2 means that you are going to add 2 or subtract 2 to each value to go 3 standard deviations. We always, even if it doesn't say to do this in the directions, you always go 3 standard deviations to the left and 3 to the right. It's just what we do. You take statistics in college, it'll be what you do. So we're going to add 2, add 2, add 2, subtract 2, subtract 2, subtract 2. So that shouldn't be something that you've got to spend a lot of brain energy on, especially because there's no decimals or anything like that. Now it says, what proportion of the area under the curve is less than 8? So here is that boundary line 8. It's an actual value on my horizontal axis. I didn't space things out very well, but what we learned last time is something called the empirical rule. And so one thing that we talked about is the percentage of the area within certain regions of any normal curve. And I told you the most beneficial thing to do would be to kind of memorize all of these little sections and the percentage that's in each section. So I'm just going to kind of go through, and I'm shading a whole entire area of interest. So everything less than 8 gets shaded, but the way I do it shows that we're partitioning that up. And it's been a while since I've seen you, but each little tail beyond 3 standard deviations from the mean has 0.15% of the area in that section right there, the area under the curve. Does anybody remember what percent is between 2 and 3 standard deviations from the mean? 2.35%, good. What about between 1 and 2 standard deviations of the mean? 13.5. And then the 2 in the middle there are 34. and 34. So all you need to do then is just add up those percentages, but just be careful, it does say what proportion. So we'll get a percent when we add all these, and we'll just need to move the decimal over a couple of times to change it to a proportion, which is a fancy word for decimal. So 0.15 plus 2.35 plus 13.5. I'm going to go ahead and just say plus 68. So 84% of the area under the curve is less than 8. So about 0.84 is going to be the proportion. We are estimating because the empirical rule is an estimation. It's not exact, but it gets us really close to the correct answer. So that's what we did last time. But today, here's the problem. So 8 was an actual value on the horizontal axis. So we knew what these little pieces were. But today I might ask you a question like this. To find the area under the curve for everything less than 3. Well, that's going to cause us issues because 3 is between 2 and 4. Okay? And it doesn't necessarily cut this slice in half because we've got some curvature up here and so forth. So we're going to have to move beyond the empirical rule to figure this out. I want you to write that all normal distributions, like the one above, are the same. All normal distributions are the same if we measure in units of size standard deviation from the mean. What I'm saying there is I can take any curve, and these values are 0, 2, 4, 6, 8, 10, 12. You've seen all different kinds of curves where those could be decimal values, positives, negatives, whatever. They're all the same if we standardize or make z-scores out of these numbers, which is what we're about to do. So I'm going to say that one more time. You can take any word problem and its picture that you draw, and if you standardize all of these values on the horizontal axis, you're going to end up with the same exact numbers. So I'm going to show you how to do that now. Here's a little formula for z-score, because what we're about to do is take the 0, 2, 4, 6, 8, 10, and 12, and we're going to standardize them and draw a new picture. Okay, so here's the z-score formula. But you guys did very well on the test with that, on the mid-unit test. So I don't think we're having trouble plugging into formulas, which is great, because in statistics you do that a lot. In this blank space right here, just kind of line up for yourself. We're going to standardize all the numbers on the horizontal axis at the top of your page. 0, 2, 4, 6, 8, 10, and 12. And we're going to see what happens when we standardize those or change them into z values. So you might have to work kind of small here. To change 0 into its z value, you're going to take that value 0, subtract the mean, which in our problem at the top of the page is 6, and put it over the standard deviation, which at the problem at the top of our page is 2. That's negative 6 over 2, which is negative 3. You may not really know what we're doing yet, and that's okay. I'm just going to switch colors so there's a little bit of differentiation here, because we're going to have to write kind of small. All right, so if I take the value 2 and I switch it over into its z value, that's going to be 2, take away the mean over the standard deviation. Well, that's negative 4 over 2. And negative 4 over 2 is negative 2. If you know what you're doing, if you're just like, okay, I see what she's doing. She's just changing all of these into z's, and you want to move along ahead of me, that's a great idea. Value minus mean over standard deviation. You have a calculator there if you don't feel very comfortable with the integers and all of that. But math is all about patterns. Sometimes you can be completely clueless about what you're doing, but you can start to notice patterns. Look at the answers we keep getting. Negative 3, negative 2, negative 1. Any predictions on what the next one's going to be? It's probably going to be 0. And sure enough, 0 over 2 is 0. well, if I'm a student who notices that, then I'm just going to, not really cheat, but I'm going to be efficient. I don't want to show all that work 3 more times. I get it. I get the pattern. So once again, I took all the values at the top of the page, all of these horizontal axis numbers, 1, 2, and 3 standard deviations out, and then I found their z-score. So here's what I did. I took that curve at the top of the page, and I standardized that normal curve. Now, label it with the new standardized values. That will be what happens anytime you take any word problem that I ever give you that wants you to draw a normal curve. If you were to standardize the values in that word problem, here is what would happen every single time. You get -3, -2, -1, 0 would be the mean, and 1, 2, and 3 every single time. It's called a standard normal curve. Look at what it says underneath there. When we standardize all the points on the horizontal axis of any normal distribution, you're always going to end up with a mean of 0 and a standard deviation. Check this out. These are all 1 apart from each other. That's the standard deviation. That's always going to happen. It's called a standard normal distribution. Now in the blanks, just because you just read it, I want you to write it and it'll stick in your brain better. On the standard normal distribution, it has a mean of 0, mu is 0, and standard deviation is always 1 for a standard normal distribution. This is just a normal distribution. If you see standard normal, then it's talking about this one with the -3, -2, 1, 0, 1, 2, 3. Okay, turn the page. Now back to the problem at hand. What I want to do in that original thing that you drew at the top of your notes on the first page is I want to find the area to the left of 3 under the normal curve that had a mean of 6 and standard deviation of 2. So we would probably need to start by standardizing the value of 3. So the same thing that we just did to the 0, 2, 4, 6, 8, 10, 12, we need to do to the 3, the value of interest, the number in the word problem that we're focused on. So if I want to standardize a value, listen to that vocabulary, standardize the value, that means find the z-score. Mean is 6, standard deviation is 2. So we might get decimal values, and that's okay, -1.5. Okay, now check this out. This is interesting. On the computer, I kind of plugged some things in and got it to shade for you. Here I have shaded everything to the left of 3. And here I have standardized all the numbers, and I've shaded everything into the left of the standardized value, -1.5. What do you notice about those shaded regions? They're the exact same. I want you to title this as normal. And I want you to title this one as standard normal. They're both the same thing. Our area of interest, that shaded portion, is the same. But here we're finding everything to the left of 3. And here we're finding everything to the left of -1.5. Now I'm showing you just kind of a little extra stuff today. We're going to do some calculator work. What we're going to do is we are going to find this shaded region right here on the normal curve. It's important that you understand we're grabbing our numbers off of the one on the left. So what you're going to do, I'm really only showing you one thing today, and it's this. So pay really close attention. You're going to hit second, so the blue button, and then vars, which is like your variable statistics. second vars. And you have this distribution menu. That's the menu we want to be on. And it says to choose normal CDF with a little open parentheses there, so option 2. And it's going to always pop up with this menu, lower, upper, what is your mean, and what is your standard deviation. Okay, look at your picture really quickly. That shaded region starts at 3 and goes to the left forever. Forever and ever and ever and ever. It doesn't stop at the 0. Remember, we talked about that. So I'm shading everything to the left. So we're actually, this is going to seem really random and weird, and I'll explain it in a minute. We're going to say that our lower boundary is actually negative 1,000. Because we want to go really far to the left. Our upper boundary is the one on the right. It's where the shaded region stops, so that's 3. So negative 1,000. The upper boundary for that particular picture is 3. What's the mean on that normal curve? What's the mean on the picture? 6 is the mean. And the standard deviation is 2. Now when you're done entering all those in, choose paste and press enter. Your calculator is going to tell you that this is the proportion of the area to the left of 3 in that curve. That's the area of the shaded region, essentially. So I want you to put that in this blank, and we'll go ahead and round, let's see, 0.067. This is the proportion of the area under the curve up here on the left, the normal curve. Now, this is really interesting. Watch what happens if you do all that calculator work over again, but we're going to type in some different things. Look at this picture, okay? We're still going all the way to the left. We still need to have our lower boundary set at negative 1,000. Again, I'll explain that a little bit more on the next page. But now our upper boundary is negative 1.5. Second period, what are you going to put for the mean of the standard normal curve? 0. What are you going to put for standard deviation of the standard normal curve? 1. Just look at your picture. If I lost you, the mean is in the middle. Standard deviation is what you're counting by. So 0 is the mean, 1 is the standard deviation. So do second vars, normal CDF. Anytime you're wanting to find the area of a shaded region, you're going to do that in your calculator. We've got our lower that we don't need to change, but now our upper is negative 1.5. For standard normal, the mean is always 0 and the standard deviation is 1. And look what you get. You get the exact same thing. So it doesn't matter if you standardize everything or not, you're going to get the same answer. So go ahead and put that in the blank right down here. You get that same 0.067. What I want you to put for what do you notice is we get the same answer the same area, whether the value is normalized or not. Here's what that means. As you're writing that down, just listen. I got the same answer whether I had taken all of the values and standardized them and found their z-score or not, okay? So you might be thinking, well, then what was the point of doing all that work? I'll answer that on the next page. So make sure you've got this written down. You got the same answer whether the value is normalized or not. And I just want to answer a couple of questions that some of you might have. Why are we using negative 1,000 as the lower boundary? It seems really random. So what I want you to write is we choose negative 1,000 because it's many, many standard deviations below the mean. We choose negative 1,000 because it's many, many standard deviations below the mean. you will always use negative 1,000 if you shade something off to the left. That will always be your lower boundary if you shade everything to the left of a number, okay? What do you think your upper boundary will be in a second when we shade everything to the right? 1,000, okay, cool. If you're a person who doesn't really understand that, that's okay. Just know that negative 1,000 and 1,000 are going to be your boundaries for a little while. The other question is, why would we take the time to do all of this work right here? Remember how we had to switch all our numbers over? Why would you do that if you get the same answer? Okay? And typical math teacher here, I'm going to tell you, you're going to need the skill of standardizing in the future, so it doesn't hurt for you to know that now. But you can choose whatever is easier for you. So I want you to just write, you will need the skill. You will need the skill of standardizing. You will need the skill of standardizing in the future. But you can use either set of values in the calculator. Your calculator can handle either one of those. In college statistics, you won't be doing this stuff in the calculator. There's this giant chart of z-scores that you have to like find a column in a row and see what nut value is there. And you do all this by hand, believe it or not. So high school version is, let's figure it out in the calculator. But at a college level, you would need to standardize. So I'm showing you that. And then you would have to find it by hand. But you can use either set of values in the calculator. So I don't care. So you're going to see that I'm going to always just take the most efficient, easy way. Here are the steps. There's not really any blanks for you to fill in there. Just kind of skim through that. You're always going to need to draw the curve, label everything, and then highlight or underline this. Draw a little picture for yourself. Mark where the value is in the problem that you're interested in and whether you're supposed to shade below or above it. Shade your area of interest. You must do that for a little while, at least for this lesson. As we move forward, if you get really comfortable with just grabbing a calculator and going to town, fine. But I want you to draw your pictures today so that you're understanding what the heck you're doing in the calculator. And then do your calculator stuff. You're going to use negative 1,000 or 1,000 for problems that have you shade to the left or right of a single value. That's the big takeaway there. So all we're going to do is practice that 1, 2, 3, 4, 5 times, and then we're going to wrap up with a little review. Okay, so that's it. That's all I'm going to teach you today. We're just going to practice. Make sure you're really comfortable with this. If you're reading this paragraph and you don't feel like reading for detail, highlight the important parts. You don't need me to do that for you. Highlight the important parts in here. If I'm a student and I kind of know what's going on, I know this is important. The mean. The standard deviation. The fact that it's normal, approximately normal. That way I know how to draw it. It's not skewed or anything. We're talking about stopping distance. Everything is in feet, so how long it takes a car to come to a complete stop. Marta's driving a car. She spots an accident 170 feet in front of her, and she needs to basically slam on her brakes. About what % of the cars, like the one she's driving, would be able to make that stop in less than 170 feet? So that's the question. And it's asking for a %. I need to make sure my answer is a percentage. What % of the cars would be able to make a stop in less than 170 feet? Okay, let's draw this picture really quickly. The drawing it is really the tedious part. But you're not really going to know what you're going to put in the calculator until you just draw a quick sketch. So the average stopping distance, the mean, the mu, is 165, and that's feet. It's always good to label things. And the standard deviation is 4 feet. So add 4, add 4, add 4, subtract, subtract, subtract. If you want to just shortcut it and write what I've written because you know how to add and subtract, that's fine. Okay, now, I want to know how many cars, like the one she's driving, kind of the same model, could stop in less than 170 feet. Because again, she sees this accident 170 feet ahead of her and she needs to stop. Well, 170 is going to be right about here. And I want to know what proportion of the cars, or percent rather, can stop in less than 170 feet. So should I shade to the left or to the right? To the left. I want cars stopping in less than 170 feet. Before you pick up your calculator, see if you can answer these things. When we do the normal CDF thing and it asks for lower boundary and upper boundary, what's the lower boundary going to be on this problem? Negative 1,000. Very good. What's the upper boundary going to be? Where did you draw your line? 170 feet. What is the mean that you're going to type in going to be? 165, right out of the paragraph. And what's the standard deviation you're going to type in? 4, right out of the paragraph. So we're actually moving into some easy stuff. If you're a person who really struggles with math, this is right up your alley. The upper here is 170. The average speed, the average stopping distance, excuse me, is 165 feet with a standard deviation of 4. Just a little thing, if you're looking on my answer key for like an assignment, look at how this looks in the calculator. Normal CDF, and then it's just separated. There's your lower boundary, comma, upper boundary, comma, mean, comma, standard deviation, close parentheses. Now it asks for a percent. So about 89.4% of cars would be able to stop in 170, less than 170 feet. That's what we're going to write. Okay, as a matter of fact, show yourself that to find that shaded region, the area of that shaded region, we did normal CDF. Our lower boundary was negative 1,000, comma, our upper boundary was 170, comma, our mean and our standard deviation gave us 0.894. So if you're looking back in your notes, you'll be reminded, okay, we just grabbed our calculator and typed this stuff in. So about 89.4% of cars like this can stop in less than 170 feet. And now we've answered the question. The reason I'm doing so many examples with you is because you need to get used to the way things are worded. Like on the next one, this might throw some of you off a little bit. Let's look at example 2. When professional golfer Rory McIlroy. Okay, see, apparently this is one of those things I should know, but I don't follow sports ball. Okay. He hits his driver. The distance the ball travels can be modeled by there's our picture, normal distribution, with a mean of 304 yards. So it didn't say mu. You had to actually kind of pick that out. There's mean yards. And standard deviation of 8 yards. So this is the driving distance. on a specific hole, Rory would need to hit the ball at least 290 yards to have a clear second shot. What percent of his drives travel at least 290 yards, and is he likely to have a clear second shot? Okay, let's draw this picture. Average driving distance for him is 304 yards. Standard deviation is 8. So I just popped those out really fast on my calculator. Plus 8, enter, plus 8, enter, plus 8, enter. 312, 320, 328. Minus 8, minus 8, minus 8. 296, 288, 280. Now, to get a clear second shot that avoids a large group of trees, he needs to hit the ball at least 290 yards. Okay, that 290 is where I'm going to draw my vertical line. So I'm going to estimate that somewhere right about here. Well, in the last two problems, we've shaded to the left. But he needs to have a drive at least 290 yards, which means 290 yards, or, hey, even better, more than that. Because then he'd really have a good second shot. So, shade to the right. Now, how does that change what you're going to type into the calculator this time? What's your lower boundary going to be? It's not negative 1,000 on this one. Where do we draw the vertical line? What's the lower end of our shaded region? That's the 290, yes. So this time, because we shaded to the right, our lower region is actually the value that came out of the paragraph, 290. Our upper is going to be positive 1,000. So lower is 290, upper is 1,000. And that's why I don't put a comma when I write 1,000, because it might get lost in all these comma separated lists. And the standard deviation, the mean is 304 yards, standard deviation is 8 yards. You'll type that in for your lower, upper, mean, and standard deviation. And then when you paste. Now, big picture, you shaded a good portion of the area under the curve. That's a large percentage right there. So it makes sense that we got 95.99%. Does he have a good chance of basically that first shot being 290 yards or more? Yes. It's very likely. And that's how we're going to word it. It is very likely. So find some empty space somewhere around there. You know how we always give our answers in a sentence. He has about a 96% chance, which is very likely, of getting a clear second shot. I'm just revisiting what it's asking me. Is he likely to get a clear second shot? Yes. So just always make sure you answer the question. And then statistics, that's going to feel a little different than past math classes. So look for your wording. So you have to read closely. You have to decide, do I shade to the left or do I shade to the right? And then check out this one. Here's something else new. Okay? So I'm not going to give you 5 examples of the same thing. On another golf hole, he has the opportunity to drive the ball into the green if he hits the ball between 305 and 325 yards. So there's this little sweet spot he's got to land it in, between 305 and 325 yards. What proportion of his drives fall in that interval? What proportion falls in this interval? That's what I would highlight. Proportion falls in the interval. The picture you draw is going to be the same one that you just drew a second ago. So I'm going to let you cheat a little bit. Put the mean from the previous example, that's 304, but I won't make you go 1, 2, and 3 standard deviations to the left and to the right. Okay? This is the same picture. Busy work there. But I want to know the percentage or proportion of his hits that he could land in this sweet spot between 305, and 325, which if we copied our numbers down from the previous page would be somewhere right in here. I want to know what proportion of his hits he would land in that sweet spot. Now, if I get an answer like 2%, then I know I did something wrong. So again, notice you shaded not half, but a good little proportion there. So before you pick up your calculator, always ask yourself, what is it I'm going to type in? What's the lower boundary line in my picture? That's the 305. What's the upper part of the boundary of this little sweet spot? 325. So you're not always going to use negative 1,000 and positive 1,000. If you're shading between two values, use those values, the smaller one for the lower, the larger one for the upper, the mean that it gives you in the paragraph, and the standard deviation it gives you in the paragraph. So eventually, and I could probably name those of you in here, eventually you're not going to need to draw the picture. You're going to know how to just pick up the calculator and do it. But for today, I want you to draw the picture. I want you to just be able to look at a word problem and decide, is this the kind where I shade to the left? Is this the kind where I shade to the right? Or is this the kind where I shade between? So again, when you shaded, you didn't shade half. This is a little less than half, so it'd be like 44.6%, but it did say proportion. So let's answer it as...
I need to see Ashton Villarreal in the attendance office, please.
Yes, ma'am. About 0.45 of his drives are between 305 and 325 yards. If it said percent, I would have probably said 44.6%. Example 4 is a sneak peek of a test question. I want you to know how this will be asked on a test. The company produces ceramic floor tiles. They're supposed to have a surface area of 16 square inches. Okay, but because of like the machinery and some other variables, the actual surface area has a normal distribution with a mean of 16.1. I'm highlighting all of the important things, and a standard deviation of 0.2, and these are in square inches. Find the proportion of tiles produced with surface area less than 16 square inches. Raise your hand if you think you can go straight to the calculator and not draw a picture on this one. Does anybody think they're ready for that? Okay, cool. Well, be on your merry little way here. Maybe you're a student who this is good enough. You don't have to label everything. If you know that you're wanting less than a 16.0, and you know that that falls between 15.9 and 16.1, maybe that's all you need to do. It's not my way or the highway, but I want you to find whatever style fits you the best, however much work you need to show for yourself, and go for it. By the time the test rolls around, I want you to be able to just pick up your calculator and go for it. Okay, second VARS, normal CDF. This time, because I shaded because it said less than 16, my lower boundary is negative 1,000. My upper boundary is 16.0, or you can just leave it at 16. The average surface area is 16.1, and the standard deviation is 0.2. Which answer choice has that as the answer? It's B as in boy. Cool. It's always nice when you get one of the answers. Feels good. Example 5 is also a test question. It'll be multiple choice, but I want to make sure that you can look at this and know what you're supposed to do. Birth weights at a local hospital have a normal distribution with a mean of 110 ounces and a standard deviation of 15 ounces. What's the proportion of infants with birth weights under 95 ounces? Maybe you're starting to feel like you can do this without drawing a picture. If not, draw a picture. There's the average birth weight. And since I'm interested in 95 ounces, I'm just going to kind of see where that is over here. So 110 minus 15. Oh my gosh, that's an actual value. Check this out. If I took your calculator away on this, you should be able to be successful, because unlike all the rest of the problems, 95 is actually one standard deviation to the left. Think about what you learned last week. Think about how we started our notes out today. So under 95 ounces are those little 3 sections all added together. So we're using the empirical rule. We don't need the normal CDF thing. Could you use it? Of course you could. But I'm going to use the empirical rule. When you add those together, you get 16%. Or if you use normal CDF, you should get somewhere right around 16% as well. So about, I'm looking back, it says proportion, so about 0.16 of infants have a birth weight under 95 ounces. Under 95 ounces. We will do the review question, which is really, really, really important because I know that it's going to be on the test. We'll do that after lunch, and then we'll be done. "95% of undergraduates have an IQ between 100 and 120. Look at how I'm going to put that in my picture. You might have done it a little differently. Maybe you didn't label the 95% yet. Maybe you didn't know that all of this needed to be in there. So this is what I know. Now the empirical rule tells me that 95% of the area under the curve is within how many standard deviations from the mean? 1, 2, or 3? Does anybody remember? Look what I'm pointing to. Within 1, 2, or 3 standard deviations of the mean. 2 standard deviations of the mean. So watch what I can do next. If I remember that 95% is within 2 standard deviations of the mean, I know that there's a tick mark between the mean and each of those values. And technically there's also one beyond that, but I don't really need that for this problem. So it helps me kind of know where everything sits on that horizontal axis. Now we still haven't answered the question. The question is, what's the standard deviation? For instance, like from here to here. It's almost like algebra from here on out. How can I figure out if each of those tick marks is the same exact space away from the next one? Okay, how are you? Yes, that's the answer. So how did you do that?
Well, 110 and 120 is 10. Just divide that by 2.
Okay. You could say, all right, from 100 to 110 or 110 to 120 is a difference of 10. When you cut that in half, because you know these are all equally spaced, then you know that the tick marks are 5 units apart, and you've just found your answer that the standard deviation is 5. And it doesn't say, I guess that's just kind of like 5 IQ points, but the standard deviation is 5. And if you're still kind of, if I went a little too fast for you, right here, 110 to 120, that's a difference of 10, and I just need to cut that in half to find how far it is from one to the next, because they're all equally spaced. So it's 5. Standard deviation is 5. Okay. Cool. Now that's it for the